Okay, so let's get started. So for the second plenary, we're so excited to have Sebastian Rubek give this talk. And Sebastian is currently at OpenAI. Before OpenAI, he got his PhD from Lille University in France, and he's been in many other places. He was in Princeton, he was in Microsoft Research, where he led the machine learning group. He has won many awards for his work, including Best Paper Awards at Colt, at NeurIPS, and at STOP. And we're really happy about this opportunity to have one of our own from the theory community who is now working on AI tell us about advances in this area. So let's please welcome Sebastian.
Thank you very much. Thanks a lot. So first, I'm really sorry that I couldn't be here in person. We just had our fourth kid 2 months ago. So right now it's pretty busy at home and it's very hard to travel on the other side of the planet. But I really want to say that, this community, the StockFox community is my favorite community of all the communities that I have interacted with. And I'm really, really happy to be here and to present to you these recent advances in LLMs for mathematics. Okay, so let's get started. There is some stuff that I want to cover. It will be roughly a 40-minute talk, give or take, around that time. And then we can move into the Q&A, and hopefully you will all have interesting and super difficult questions for me. So let me start with some disclaimer. First of all, I am an OpenAI employee. That is just a fact. However, in this presentation, I'm really coming to you as a scientist, and what I'm trying to do is to present as fairly as possible the current state of those models. How good are they at doing research? How good are they at mathematics and theoretical computer science? In particular, nothing that I will talk about here requires me to be at OpenAI to tell you those things. Anything can be done from the outside. You can repeat any of the experiments that I will tell you about. So that's point number one, which I think is an important point. Second point is, out there, everybody talks about benchmarks, and this is, a key driving force of the field is to try to get better benchmark numbers. I will not talk about benchmarks at all. There will be 0 benchmark numbers. If people are really hungry for benchmark numbers, I just give, a few in there in this slide, and that's all I'm gonna say about them. So the benchmark are like on AMY, which is this kind of exam to get into the IMO, so like high school competitive mathematics, models like GPT-5, they get 100%. It used to be that, 1 year ago, 1.5 years ago, they were getting 10%. So that's kind of the progress. On frontier math, the tier 1 to 3 question, we're roughly at 40%. We're probably going to get to 50, 60, in very soon. And on tier 4, we're at 15%. If AMY, frontier math, tier 1 to 3, tier 4 don't mean anything to you, let me just give you some example just so that we're on the same page. So this is an example, just on Wikipedia of an AMY question. So you have a 3 factorial, factorial, factorial over 3 factorials equals k times n factorial. And you have to find what is the value of k plus n, given that n is the largest number that satisfies this. Okay, so any of you in the room, if you think for maximum 2 minutes, you will solve this question. This is very easy. 3 factorial, factorial, factorial is not such a big number, so it's very easy. What about, so again, our models, they get now 100% on this type of question. What about this frontier math benchmark? So frontier math is let's say this is an example of a tier 2 question that you see. So it turns out, here is a claim, that there are constant C, alpha, and beta with the following property. Is if I have integers a, b, c, d, e, such that a times b plus 1 is equal to c times d times e, then the number of solutions to this equation, when the product a times b is less than x, so the order of magnitude of the left-hand side and right-hand side is x, then the number of solutions to this equation is asymptotic to c times x to the alpha times log to the beta of x. And the question in this benchmark, to make it like a nice round number that you have to compute, is to compute 1000 times c. Okay, so that gives you a number, and it's very easy to grade whether the model is correct, and it's also very hard to guess the right answer. This question, for example, I have no idea how to solve it. Okay, this is, as far as I'm concerned, a very difficult question. Turns out that in this case, actually, the answer is in a paper from 2016 in analytic number theory. And basically, I think the creators of this benchmark, what they are trying to test is whether the models they have understood this 2016 paper, not whether they can, rederive the result on their own, but whether they have understood the 2016 result and are able to kind of regurgitate the right constant in this case. So the models right now, they are around 40% on this type of question, which I think is already quite impressive. And the tier 4 is really research level questions. Okay, so that gives you a first kind of very, very rough impression of the field. And the goal of this talk is going to go to try to go much more deeply into the qualitative properties rather than these quantitative properties. Final disclaimer is that, the content of this talk can provoke very strong emotions. I was contemplating on this introductory slide to put, some of the insults that were thrown at me in the last few years on X and other places, but then I thought maybe it's bad form to do that. But let's just say that what I'm going to talk about does provoke a variety of emotions, and I'm sure it will be the case for the audience too. Some of this emotion is provoked by the really deep implications of this content, I think, and we will touch on these implications towards the end. Okay, so we'll come back to it. We'll not leave it untouched. Okay, so what's the agenda more precisely? We're going to start with a very soft, light-hearted start where we're going to see the evolution of the model's capabilities through images. Okay, it's both kind of a slightly non-serious and fun way to begin, but there is actually something more serious hiding behind, which I will try to explain. Then we'll get into the heart of the matter. I will give you 3 examples of LLM results in convex optimization, combinatorics, and probability theory / statistics, which is, of course, the field that I'm personally the most familiar with, and that's why I chose those fields. Then I will not only talk about positive things, I will also give you 2 examples of failure cases, which I think are very important and are important to keep in mind when you interact with those models. And then we will conclude with a brief discussion of the implication for the future, as I said, and finally go into Q&A. And one last point that I want to say before we move on into the actual content is that this is, of course, an AI presentation about the capabilities of the models in mathematics. But I think the math results are actually quite interesting and kind of fun, at least to me. Of course, they are related to things that I did before, so that's probably why I find them interesting. But hopefully, just purely the mathematical results will be of interest to at least some of you. So it's not just an AI talk. All right, so let's get started with the lighthearted version of the presentation. So this is, of course, Le Petit Prince, and you all know in the book when Le Petit Prince meets the pilot, what the Little Prince asks is to draw a ship, okay? And what we're gonna do is we're gonna do the same thing. Whenever we meet a new unknown entity, like a new LLM, we're gonna ask it to draw a ship, okay? Of course, drawing a sheep, for many reasons, it's not the best thing to ask. We're going to do a variant, which is a little bit more fun. We're going to ask it to draw a unicorn. And to make it even more interesting, we're going to ask to draw the unicorn in TXZ. I know all of you in the room have been battling with TXZ probably in the past, maybe much less so now that we have LLMs, but trust me, before LLMs, it was a pain. And the reason why we want to do unicorns in TXZ is to make sure that it's out of distribution, that it's really something that the model cannot have seen at pre-training time when it was going through the web. Of course, already that sentence got me a lot of flack over the years where people say, but you don't even understand the diversity of things that are on the web. Who knows? Maybe there's some dark corner of the web where there is a unicorn in TXZ. It's possible. It's possible, but what I can tell you is after 3 years since that example, nobody has been able to show me a TXZ unicorn on the web. The only thing that came up is this duck unicorn, which I will concede is a unicorn in TXZ. But keep in mind this image and see whether you find the LLM unicorns to resemble in any way the duck unicorn. Because in a sense, if I tell you that on the web, And this is where, it gets like it's fun, but it's also like slightly more serious. If I tell you that on the web, the only example of unicorn in TXZ are duck unicorns, but then at test time, when I ask it to draw a unicorn in TXZ, it does not draw a duck. That's a huge, like, that's a big piece of information that tells you something about the generalization capabilities of those models. So anyway, let's get into it. So let's watch the evolution of the TXZ unicorns over the last 3 years. So it starts with GPT 3.5. So I think, this is, roughly 3 years ago. This was the unicorn that GPT 3.5 would draw. At the time, I was personally floored that it would produce, latex that compiles. I mean, this is what we're talking about 3 years ago. Just writing, you understand? It's a machine that just predicts the next word, and it's predicting next token and producing code that compiles. I was just absolutely floored by that. But not only that, but you see that it's trying some kind of horn on it. Okay, so I at the time I was already like, this is when I became, I guess, convinced that this is on a path to something good. Is really with this image. Then a few months later, GPT-4 came, and this is what the unicorn became. That's like really next level in my opinion. You see that it understood all the elements of the unicorn. It drew the horn. It's trying to do a mane. It has the color scheme right. I mean, it's just like this is an astounding image in my opinion. Then you move to GPT 4.5. It has been widely reported in the media that GPT 4.5 is, of course, a bigger version of GPT-4, and GPT-4 was a bigger version of GPT 3.5. But all of this is pre-reasoning models. So you see this evolution, you can really see this is purely scale. And again, I think as theoretician, trying to understand this evolution remains to me the major open problem that is, I think, potentially attainable by theory, is to understand how is it that by training bigger models on a web-like distribution, you get this evolution in your TXZ unicorns. Very, very hard question, but I think not totally impossible to answer. But then we moved to the reasoning era. So now this is GPT-5 this summer, so not that long ago, like 5 months ago, something like that. And I think the level of details is a huge step up. Of course, now the model is thinking. Okay, so the previous unicorns, they were like direct response to the prompt. Now the model is trying to think. There is some hidden chain of thought. It's trying to do many different things, and then finally it outputs to you TXZ code that gives this unicorn. And finally, just last week, we came out with GPT 5.2, which is another improvement on the series of model. And this is the new unicorn. And when I look at this new unicorn, you can debate whether it's prettier than the previous one or whatever. But what I pay attention to is more like the fact that it's trying to be much more delicate in how it's drawing. So instead of having these legs that are very straight, very simple rectangles, it's now trying to have these curves that are more interesting. It's trying to have shading for the hooves and all of that. So it's really trying to get more and more complex. So I find this evolution very interesting. But now let's get back to what we want to talk about, what I think you are all interested in, and also what I'm interested in. I'm not that interested into TXZ unicorns, which is mathematics. So let's try to see side by side the evolution of TXZ unicorns versus the type of math questions that those models are able to solve. So 3 years ago, GPT 3.5, this is the type of question that we were using to evaluate the models. Brian is a frog, Julius is a swan, blah, blah, blah. Bernard is a rhino, Bernard is green, and whatever. There is some stories there, and then you ask what color is Lily. And Lily is a frog, and she should be green. Okay? So this is really like completely stupid. It's just to test whether the model is able to even understand what is written in the prompt. Really just understanding of language and very, very minor, thinking. Came GPT-4, and we started to be able to ask actual, mathematics questions. So I would say the top one is kind of an elementary grade question. The bottom one now, or the middle one, is maybe I don't know, a middle school question, or something like that. Middle school question, let's say. So you have, g of x is f inverse, then I give you the value of g at a few points, and I ask what is the composition of f 3 times at 6. So you just have to move, the F inverse on the other side a few times. So you just have to be able to do a chain of reasoning. This is the type of question that we're asking for GPT-4. And to be sure that everybody in the room remembers, when we wrote the Sparks of AGI paper 2.5 years ago, this was one of the flagship examples, this equation. It looks completely stupid from today's standard, but back then it floored many of us, certainly me. So now what is the equivalent today with GPT 5.2? So this is a theorem that GPT 5.2 proved, I think, two weeks ago, which I will explain in a little bit more detail. So it's telling you something about it's about estimating a covariance matrix in a Gaussian model, and it giving you the closed form formula for the risk, the forward KL risk for a given unknown covariance sigma star. And this involves a d gamma function. And then the key thing that we asked the model to prove was that this loss function is monotone. So if you add more data, the loss is going down, which was actually an open problem from Colt in 2012. I will come back to all of this, but basically GPT 5.2 just proved this theorem. So this is the evolution that we're talking about. And I'm not going to be in this presentation in the business of telling you what would the presentation look like a year from now. This I will leave to the audience to make their own, idea of what's going to happen. So let's dive a little bit deeper and let's look at a few examples really much more precisely. So I will start, the first example is going to be about convex optimization and rederiving, okay, so not doing something new, rederiving a known recent result in convex optimization. So what is this known recent result? So let me just make sure we're all on the same page in the basics. If you do gradient descent on a convex function which is L smooth, meaning that the gradient map is L Lipschitz, then the learning curve, so as you keep optimizing, you look at your loss function and you look at how it's going down. So the learning curve is monotone, so it's going down, if and only if the step size of gradient descent is less than 2 over the smoothness, 2 over L, okay? And, the if part is to show that if your step size is smaller than this, then you have monotonicity. And the only if part is you show that if your step size was bigger than this, then there is an L smooth function such that your loss is not going to be monotone. Okay, this is the most classical result in convex optimization going back to the 50s. Now, much more recently, in March of this year, Barzilai, Shamir, and Zamani, they showed that the learning curve is convex. So not only is it decreasing, but actually it's tracing a convex function if only if the step size is less than 1.75 over L. Okay, there is, for some reason, 1.75 over L is what appears. Now, what is interesting about this result is that the paper has a V1, a V2, and a V3 on arXiv. The V1 was not able to prove the tight upper bound of 1.75 over L. The V1 could only show that if the step size is less than 1 over L, then the learning curve is convex. And if eta is more than 1.75 over L, then the learning curve is not convex. Okay, so there was a gap between 1 over L and 1.75 over L. So it gives a really ideal setup for a controlled experiment. I also know that this paper, cannot be in the training set for GPT-5. I mean, it's before the cutoff date that we have for the model. So I knew it's not in the training data at all. And it gives a very nice and easy setup where I can give the V1 of the paper. I'm not even asking it to prove anything from scratch. I'm giving it the V1 of the paper and I'm asking, can you now close the gap? The V1 gives 1 over L. Can you, improve it? And I'm not going to ask to improve it to 1.75 over L. I'm just asking to improve it. So this is literally exactly what I did. No modification. I put the PDF, I attach the PDF of the V1. You see it says V1 here. And I say, can you improve the condition on the step size in theorem 1? I don't want you to add any more hypotheses. I just want you to work to improve the step size condition under the same assumption as theorem 1. And it thought for 17 minutes. And it comes back and says, yes, under the same assumption, I can prove eta less than 1.5 over L. So it didn't quite prove the 1.75 over L, but it improved from 1 over L to 1.5 over L. Okay, so that's the first example, which I view it as it was at a time, at least at a moment in time, going beyond what was proven in that paper. So let's look at the proof, because of course we have to verify the proof. We're not gonna trust GPT to just give us correct results. So this is the proof. We don't have time to go into details, but it's somewhat standard. So the original proof of the humans in V1 was using co-coercivity, which is one of the key like basic properties of smooth convex function. It was using it once. And basically, GPT read the proof and realized that if you massage things a little bit, then you can use co-coercivity twice in two different places. And if you use it into two different places and recombine the result, then you improve 1 over L to 1.5 over L. But the V2 proof by the humans was not like that. It was not just using it twice. It was much more clever. It was basically setting up an optimization within the proof to optimize the linear coefficient of many different inequalities so that when you combine them with the right coefficient, you're going to get the 1.75 over L. Now, it turns out that I redid this experiment with GPT 5.2, and I did not even give it the paper in context. I just straight up asked the question. You have an L smooth function. What is the condition on the step size so that the learning curve is convex? And it thought for 20 minutes, and it came back with both the upper bound of 1.75 over L and a counterexample when eta is more than 1.75 over L. How did it do that? I looked at the proof, and the point is now this time around GPT 5.2, for reasons that I can't get into in this talk, in part because I want to assume that I can give this talk as if I wasn't in OpenAI. But this time, GPT 5.2, it knows this paper of Drury and Tebul from 2012, which is the paper that introduced this idea of doing optimizations within the proof of optimization proofs. Which is a very nice trick that makes a lot of sense. And now GPT 5.2 knows this trick and was able to use it to get the optimal result. And not only that, but it also wrote code, in the same, like I just asked the question once, I didn't ask it twice. In the same chain of thought, it both proved the upper bound with the Drury and table trick, and it wrote code to search for counterexamples, code that looks like this. And by using this code, it was able to search for counterexample and to find one. Okay, so this is just example one that I wanted to give you. Now, let's move on to a second example in a completely different space, although convexity will appear again. So this is a combinatorics problem. Let me kind of set the stage for it so that we are all on the same page. So there is this extremely basic question which goes back to more than a century ago of understanding what are the constraints between different subgraph densities. Okay, so the very basic result of Mantel tells you if you have a certain edge density, what is the triangle density that you're going to get? At which point are you forced, if you have a certain edge density, to have at least one triangle? Okay, but more generally, you might be interested in the relationship between edge density and triangle density, or any collection of subgraph densities. Now, this type of question is extremely difficult. For one, it's actually undecidable, even for a given linear inequality between subgraph densities, to decide whether this linear inequality is correct or not. This is, in fact, undecidable. This is a result from Hatami and Norin from 2011. But this is for general subgraph densities. The most basic version of the relation between edge density and triangle density, this has been completely resolved by Rasborov and others, I guess something like 15 years ago or something like that. And it looks like this. So, if you have a certain edge density on the x-axis and the triangle density on the y-axis, then not any point in this two-dimensional plot is feasible. You have some constraint. If you have a given edge density, you're going to have some constraint on the triangle density. The upper bound is a famous upper bound of rho to the 3/2, where rho is the edge density. So you can't have anything up there. And the lower bound, this is a Rasborov lower bound, which is a complicated lower bound, but basically it's piecewise. You have a curve which is piecewise here, and the curve is non-linear, like there is some slope to it, you can see. And basically any point in there is attainable. Okay, so this is the relationship between edge density and triangle density. You see that it's a very non-convex relationship. Okay, now what are we going to ask GPT? Okay, these are really two difficult questions. So first of all, this is already an important statement. I'm not going to ask any question like this to GPT. This is way too difficult. But I know easier version in that space, things that I have thought about myself that I know are not that difficult, that where I spent, a month or so thinking about, I could make some progress, but not the whole way. I'm going to ask that type of question. So again, calibrating yourself when you work with those models is, of course, very, very important. So here is how I'm going to calibrate myself. Instead of graphs, I'm going to be thinking about trees. And it turns out that with Nati Lineal, more than a decade ago now, we showed that for trees, so if you are interested in subtree densities within large trees, instead of subgraph densities within large graphs, then whenever I draw a picture like I have on the right-hand side of constraint between those different quantities, this picture is going to be convex. So trees are a much nicer world where we have convex sets that appear. And the very basic question is, what will this convex set look like in the equivalent of this edge density versus triangle density? Now, what is the equivalent of edges and triangles, like of the simplest kind of structure in trees? Of course, triangles there are no triangles in trees. So what is the equivalent? Well, I would say that the most simple thing is a pass versus a star. Okay. By the way, of course, a triangle, the more general version is a click. So you can ask, the same right-hand side plot question for edge density versus clicks, which has been done later. But anyway, so here for trees, we're going to be interested in paths versus stars. And the first non-trivial case is going to be with 5 vertices, right? Because if I have 3 vertices, then a path and a star is the same thing. If I have 4 vertices, then a path on 4 vertices and a star on 4 vertices are 2 different objects, but these are the only 2 subtrees on 5 vertices. So the sum of them is 1 and that's it. But if I go to 5 vertices, then I have 3 different subtrees with 5 vertices. So the question starts to be interesting. Okay, so this is a star with 5 vertices, a path with 5 vertices, and the remaining isomorphism type on 5 vertices is this Y kind of figure. Okay, so now I can ask myself to do the same plot where I'm going to have the density of stars versus the density of paths. Okay, what we conjecture in the 2013 paper is that the convex set that corresponds to path densities versus star densities is what's between these 2 blue curves. Okay, and if you're interested like this lower envelope is what you get by convexity, where the diamonds point, they are given by this millipede. So here, imagine this as degree D. So you see that as D gets bigger, this has more and more stars as a function of the total number of subtrees in it. So as D increases, I get higher and higher, with the fraction of stars versus the fraction of trees, okay, versus the fraction of paths. So this is what we conjecture in that paper. And the only thing we were able to prove is this red line here. So this was the lower bound that we were able to prove. So we were able to prove that this convex set is above this red line, okay? But we were not able to prove any of those inequalities. All right, we're almost getting to the AI question. Sorry that it's a little long. So the first inequality, so this first part of the convex set, we were able to prove it with students at Princeton a few years later, and it corresponds to the inequality that the total number of Ys is less than 9 times the total number of stars, plus P, which is the total number of paths, plus 6. So this is a universal bound for trees, and it turns out to be tight. So it's one of the constraints that defines the relationship between path densities and star densities. In that paper, we were also able to disprove all the other inequalities. So all these other, faces are not correct, except for the second one. And just if you're interested, how you disprove it is you construct more complicated millipedes like the one at the top. I'm not going to get into that. What remained open was the second inequality. Okay, so we were not able to disprove that this second little piece here is also tight. And this corresponds to this inequality. 29 times y is less than 42 times s plus 144p plus constant. I'm not speaking for Nati, but I spent a good month trying to prove this, and I gave this problem to several students at Princeton over the years, and I think the combinatorics community looked also a little bit at this question, and no progress was made. So what we did is I thought this is the right level of a question for GPT, but maybe not straight up. So what we did is we have a scaffolding on GPT-5, which I'm not going to tell you what is the scaffolding, but any one of you could come up with it. This is not that complicated. You can just imagine building some multi-agent system that is making API calls to GPT-5, where maybe there's one agent that proposes a proof, another agent that kind of critiques the proof, and so on and so forth. It's not that hard to imagine. There are many papers doing such scaffolding. I don't think the details matter too much. So GPT-5 with this scaffolding was able to think for 2 days. And at the end of those 2 days, first I was a little bit clever. I did not ask it to prove this inequality straight up. I asked it to first prove the first inequality, which I knew was correct. So I asked it to reprove this first inequality. It came up with a proof which was very surprising, different from the proof we had in that paper. I mean, honestly, much more beautiful. I mean, based on some miraculous identities that I don't know where it came from. It was able to reprove this first inequality. Now what I did is that I gave this proof of the first inequality in context and let it think for another 2 days, and it came with the proof of the second inequality. Okay, so this is just like a completely, genuinely, 100% new result obtained by GPT, but with some help from my part, kind of directing it. And I will skip the proof because we don't have time. I want to get into the Q&A. But the proof is very nice, and you can find it in the papers that I will cite in a minute. Okay, let me quickly go over the third example, which is going to be in probability theory and statistics. So this is an actual, bona fide open problem. I mean, the previous one also was an actual open problem that was mentioned in the literature, but this one was published in Court in the Conference on Learning Theory in 2012 by Ramon and Commandant. It's about the preferential attachment process. So what is the preferential attachment process? You remember, so it's going to be a tree again that is growing over time, and it's a random tree. So let's say I have a tree fixed, already it has n vertices. I'm going to add a new vertex, and it's going to connect to an existing vertex with probability proportional to the degrees. So a high degree vertex is going to attract more connection. That's a classical preferential attachment process. What these guys asked is, let's make a modification where we're going to have an attractiveness parameter W. So when a node is born with already 1/2 with attractiveness 1 or with attractiveness W. And now you attach with probability proportional to the sum of the attractiveness of your neighbors. I will let you decide for yourself what kind of processes in real life it models, but I think there are many such processes in real life. So, the more attractive friends you have, the more attractive you become yourself. But importantly, it's not a function of your own attractiveness at all. So it's kind of a pretty delicate question. And what they ask is, if I give you a large tree like this, can you estimate what was W? Is there, does this parameter W actually matter, or do all of those trees look like? Okay. And this is just for fun, an illustration, not by AI. This is, too beautiful, I think, to be done by AI. This is by Igor Korchemsky, who is really fantastic. This is a randomly growing preferential attachment tree. So anyway, we gave this open problem to, again, the scaffolded version of GPT-5. Now you might ask yourself, okay, why this open problem? Where did you try 1,000 open problems and one of them came back positive and that's the one you're talking about? No, that's not what happened. We opened a random court open problem, book or proceedings, and this is the first problem that came up. Now, I looked at it, and it turns out that I worked on the preferential attachment process, like a decade ago or something. And so I knew that there was a lot of development around similar questions, such as the finding Adam problem, which I will not talk about now, but it's a related problem. So I thought, okay, maybe it's an ideal scenario where a lot of progress has been made since 2012 on similar question. So maybe the model can leverage all of this progress and revisit these old questions that probably not many people looked at. So that's what we did. Okay, so it's the first court open problem that we decided to do, and the model solved it. Not only did it solve it, so it solved it with this theorem. It proved this theorem, which so L of t is the number of leaves. So L of t over t is a fraction of leaves in the tree. And what GPT-5, the scaffolded GPT-5, has been able to prove is that the limiting fraction of leaves is a function of W. So it's 3/4 with a correction in 1 over W, 1 over constant over W. Okay, so that's what it was able to prove. Now, let me say that it's not at all obvious that looking at degree statistics is going to be enough. In fact, there is a very nice paper, sorry, it should say 2023, this is from just 2 years ago, by Benamu and Velona, who showed that in a very related scenario, which is a uniformly random recursive tree. So that means that you attach randomly to any existing vertex, not with probability proportional to degrees of attractiveness, but now you have types. You have the type 1 and the type W, and you just attach to your own type with slightly higher probability. Okay, so it's very, very related, very similar. And there they showed that degree statistics cannot work. The proof, which I will not show you right now, is pretty non-trivial, and it leverages, very recent, last 20 years stochastic approximation tools. And what's more is, before reading the proof, I was like, okay, this proof looks complicated, I'm not sure I want to read it, it's probably going to be wrong. So what I did is that I asked GPT-5 to run a simulation of this process and to compare what was the fraction of leaves that it found to the formula that it predicted. Okay, and this is what it came back with to me with is this plot where in blue you have the predicted fraction of leaves, and in yellow is the estimated fraction. Okay, this type of project is, in my previous life, it would have taken a good month of work, I think, something like that, where I can really see myself, thinking about such statistics, spending a lot of time proving that it works, and then also spending a few days getting the simulation to work and running it. All of this was done in an afternoon. Okay, so that was the third example. Now the failure case. Okay, I won't describe, you can read if you want this statement, which is a very nice new recent result in convex geometry. But the point is, after proving this result, it's a very natural result, they ask themselves, okay, now we have proven this new result, but is it anywhere in the literature? This looks like something pretty standard. And what GPT-5 was able to do is to realize that there is a paper by Papadimitriou and Yanakakis from 2000 actually, that has the same result up to a log factor, but it's a completely different language. If you look at these two results, like just their statement, it's impossible to tell that they are the same. You really have to go in there, understand what are the concepts that are being defined. The right-hand side is about some multi-agent Pareto optimality, nothing to do with convexity. This is a special power of GPT, is to find those hidden connections. But, so that's not a failure case. What is a failure case? Well, the failure case is that this kind of literature search is really far from 100%. And sometimes the model can be inspired by things without really telling you that it's inspired by those things. So there is one example that I'm not going to go into detail, where we gave a coding open problem, or so we thought that it was open. And GPT just completely wowed us by coming back with a correct solution, which was very, very elegant. And then we later learned that this solution is almost a verbatim in a paper by Noga alone. So no surprise that it was very elegant and very beautiful, but it's not at all GPT-5 original. And if you ask it, GPT-5, it didn't tell you, where it was coming from. So you have to be a little bit careful. Another type of failure case is to miscalibrate yourself. So this is another question that I really like. How long can be the path of a gradient flow on a convex function? So you have a convex function, you do gradient flow on it, and you're going to measure the length of the trajectory. And let's say it stays within the unit ball in dimension n. And the question is, how long can it be? So this is, the illustration that GPT came up with for this question. This question is way too difficult for GPT-5 level models. What's very annoying is that it comes back with interesting looking construction, which all fail. And it takes a lot of time to check this. So this is a real problem. And this is where you both have to calibrate the kind of question you ask and also calibrate yourself on what kind of answer you're going to be able to evaluate. One possible way out of this, which I won't talk, it's outside the scope of this presentation, is to ask the model to come up with a lean certificate. There is a lot of activity in this direction. This is very, very interesting, but I don't have time to talk about it now. Okay, so all of those examples and more, you can find it in this paper, Early Science Acceleration Experiments with GPT-5, with a lot of fantastic co-authors. I will just very quickly tell you a little bit more about what's in there. There are examples in biology, in theoretical physics, about the symmetry of black holes, in material science. There is a section by Tim Gowers with two very beautiful exchanges between him and GPT-5. One of them that I just want to share with this group, which is about the unplanted click problem. So you all know the planted click problem. Now ask yourself, so in an Erdős-Renyi, the largest click is going to be like 2 log n. Now let's say I give you a graph which has no click larger than 1.5 times log n. So I have removed all of the large click. Can you tell? Okay, because efficiently you can find a log n, 1 times log n size click. So if I tell you that all of the click above 1.5 times log n are removed, it's not so obvious how you can tell that. And so Tim was exchanging with GPT-5 in the following mode. He was proposing an approach to the problem, and GPT-5 was telling him why it's not going to work. And that way, he was just able to prune out, many different directions, which I thought was really, really fascinating. There are two, another topic very, very dear to my heart, which didn't appear yet, is online algorithms. And in the paper, we have two new results by Christian Koester in collaboration with GPT-5. So of course, Christian is amazing. So, a lot of it is due to him. But as I will explain, GPT-5 did have a pretty strong contribution to. So he was thinking, for example, about the lower bound for convex body chasing in dimension 2. And he had some idea of construction. You can see it here below. And GPT-5, while thinking, it came up with pi over 2 in its thinking process, but then GPT-5 discarded it. And somehow when Christian, of course you need to be Christian, when Christian saw this pi over 2, he was like, oh yeah, that's interesting. Now it makes me think that there is a modification to the strategy. And then he modified the strategy, he still didn't know how to complete the proof, and then finally GPT-5 completed the proof. Another example, which is more straight up, is follow the leader for nested convex body chasing. I won't explain all the detail, but basically there was a question whether this is a competitive algorithm or not. Christian just asked the question straight up. GPT-5 came up with a solution. You can look, this drawing here, this TXT drawing is the construction that GPT-5 came up with. This type of question, just so you know, I will leave the person unnamed, but there is a student who spent some amount of time, a PhD student, some amount of time resolving this question. So, this is not a trivial question by any means. I should also say the connection on the previous slide, here, between the Papadimitriou and Yanakakis problem and the convex geometry problem. This convex geometry problem appeared in theoretical statistics, and there is an entire PhD thesis from MIT on the topic that completely missed this connection. So these are not like, trivial things by any means. There is a lot of Erdős problem examples by Mark Selke and Mehtab Soni. This is too complicated of a topic for many reasons. You can just read it in there. Many of the solutions were found in the literature by just finding clever connection like I showed before. There is one example of a brand new Erdős problem solved. It's a collaboration between Mark, Mehtab, and GPT-5. And there are lots more examples, more coming out every day. I mean, there is Amin Karbasi on combinatorial optimization. There is Ernest Rioux on the last iterate convergence in Nesterov accelerated gradient descent. There is Edgar Dobribran on robust density optimization estimation with Wasserstein distance and a lot more. Okay, let me conclude and then move on to the Q&A. So I think hopefully I have convinced you that starting with GPT-5, I think we have models that now can do research level mathematics. It's roughly at the level of a starting grad student. Probably there are many grad students in the room right now who are much better than GPT-5. I'm absolutely sure of it. But it's roughly at that level. It's definitely not at the stock FOCS level yet. Okay, so it hasn't proven any result, as far as I know, that would meet the bar for a stock FOCS. One concept that I find useful, to think about what's happening is this concept of AGI time. So I think in mathematics, we moved from AGI minutes in 2024. For example, I showed you this Amy problem. I told you, you would solve it in 2 minutes. That's kind of what I mean by AGI minutes. To now, today, at the end of 2025, AGI day/AGI days. That's where we are. Of course, the question on everybody's mind is, will we prompt P versus NP? Will we just ask, 10 years from now, hey, is P equal to NP, and it will solve it? And I think when you start thinking about those questions, in my mind, it becomes important to remember why we're doing what we're doing. we're not after just, the competitive aspect of solving problem before another human solves it. Like that's not really what matters. What matters to me, at least in theory, is that we're building tools that help us conceptualize the world we live in, that gives us tool to kind of abstract away many complexities of a situation and focus on the key aspect. What matters when Shannon introduced entropy was not to prove new theorem. It's the concept itself of entropy. Now, how do you validate that the concept of entropy is useful? Well, it allows you to solve new problems. That's one way you validate. But really, this understanding piece, that's the key. The key is not to write papers and to solve more problems than your neighbor. That's not what matters. What matters is that we understand the world we live in better and better and better. And I think there is maybe a chance, maybe at least an opportunity to kind of claim back this understanding piece of science as opposed to just having more and more results. And finally, the last thought that I want to share is there are some discussion about does it mean what do I tell my kids? Does it mean that they shouldn't learn mathematics? That we shouldn't be teaching? We shouldn't be researching? I mean, it's quite obviously. I think it's obvious that it's completely the opposite. I mean, the only way for us to kind of keep up with those models and also to use them as well as possible is to become more and more experts. I mean, the value of expertise only went up when Tim Gowers is, talking with GPT-5 about the unplanted click problem. He has to be able to validate what, GPT-5 is saying. So it's just like for us as human beings, when you want to collaborate with somebody who is really, really great, well, you have a lot of work to do to get to their level. So there is a little bit of that aspect. Okay, I'm going to stop here and take some questions.